Hello students, in this video we'll discuss the idea of a basis of a subspace of Euclidean space. Let's suppose that V is a subspace of some Euclidean space Rn. We say that V1 through Vk is a basis of V if two conditions are true. If number one, V is the span of V1 through Vk. And of course, recall what the span is. The span is just all possible linear combinations of these vectors, right? So in other words, this is just the set of all lambda 1 V1 plus lambda k Vk, such that lambda 1 through lambda k are real numbers, right? Okay, so V has to be the span, any linear combination. Any element of V has to be a linear combination of these elements of V1 through Vk. And number two is that the collection V1 through Vk is linearly independent. V1 through Vk is linearly independent. Okay, great. So what does this linear independence tell us? Condition 2 tells us that there are unique representations of any V in terms of these Vk. So a proposition is let V1 through Vk be a basis of V, then every element V capital, V and V capital is a unique combination, linear combination of V1 through Vk. Okay? Of course, the proof of this is relatively straightforward. Here's what we're going to do. So to prove this proposition, the proof goes as follows. Proof: if we write V as lambda 1 V1 plus lambda k Vk, right? I can do this because V is the span of those elements. And let's suppose that V had another representation, sigma 1 V1 plus sigma k Vk, right? So in other words, if I had two representations of V in this spanning set, then I can subtract these and get that 0 is lambda 1 minus sigma 1 V1 all the way down to lambda k minus sigma k Vk. And now by the linear independence, I know these things are linearly independent. That's condition number 2, linear independent. So this is going to force over here. This forces the coefficients to be 0. This forces lambda 1 minus sigma 1 to be 0, lambda 2 minus sigma 2 to be 0, etc. Lambda k minus sigma k to be 0, and we have that the lambda k's are the sigma k's, and we're done. So there's a unique way of representing any vector in the vector space, in the subspace of Rn, in terms of this basis over here, right? And of course, what are the quintessential bases that we want to think about? So of course, the quintessential basis is the basis in Euclidean space. So note. And so of course, we can also recast these things. So of course, what does 1 say? So 1 says that this matrix V1, Vk. So if I put those elements of the span in this matrix over here, has null space of just the 0 vector. The only way we get these things is that's number 2 actually. Number 2 says that the null space of that thing is a 0 vector, and number 1 says that this matrix over here, Vk, augmented with anything in the subspace, is consistent, right? Okay. And of course, for square matrices, it's easy to see. For square matrices, as a remark, so if we have a square matrix over here, so in other words, if this matrix over here, V1 through Vk, if this is a square, if is square, then call it V. Call this thing over here V. If it's square, then the vectors V1 through Vk form a basis. Well, if and only if V is invertible. Okay? And that follows, of course, from our previous characterizations of invertibility. So in other words, we're going to consider these bases as we consider a subspace of Rn, and if we check that that subspace contains vectors which is a span of a collection of vectors which are linearly independent, and that collection of vectors spans the subspace, then that will be a basis for the subspace. In further videos, we'll see that for these subspaces, there's an invariant numerical quantity called the basis, called the dimension, and that dimension is going to be an invariant quantity based on the dimension, based on the basis of elements. So we'll see that in further videos, and we'll also see examples of how we can prove that certain collections of vectors form a basis. Thank you very much.